My name is Dave Klein, and today I'll be talking about real-time event streaming, or data streaming, or whatever you want to call it, with Python and Apache Kafka. I'm a developer advocate with a small company out of the UK called Quix, and we produce an open source data streaming library for Python called QuickStreams, which is not the focus of this talk, although I will mention at the end if I have time. So what we're going to mainly talk about is how to do event streaming with just plain Python. So first, let's talk about what we're talking about here. So when we talk about event stream or stream processing in general, we're talking about data that's coming into a broker of some sort. In this case, Apache Kafka, but we'll mention there are several other options as well. That data can be coming from any kind of sources, and it can be coming in at a high rate of speed and a huge amount of data. It's not uncommon to have millions of records per second coming in from some systems. And it comes into these brokers. As it's coming through, we have our streaming applications that will do whatever processing or transformation that we need to do with that data, and then downstream systems can take it from there. So this is mainly a middleware layer, really. It's something that happens usually in a pipeline, maybe for machine learning applications or for just feeding data warehouses or different things like that, or often for event-driven architectures, event-driven microservices, and things like that. So, as I said, Apache Kafka is probably the most common broker to play that middle point. But there are some others out there, like Apache Pulsar, and Red Panda, and there's even AWS Kinesis, and there's a bunch of others too. Those are probably the most popular ones. But really, the most popular and the de facto standard is Apache Kafka, so that's what we'll focus on today. Boy, I have an echo. Okay, I'm sorry. So then we also talk about the processing. There's the brokers, that's a key part of it. There's also something that does the actual stream processing of the data as it's flowing through the broker. And so for that, there's things that are like Apache Flink or KSQLDB, which are applications that you run. They're servers that you run in a cluster normally. You manage that cluster, and then you build and deploy jobs to run on those clusters to do your stream processing. And it's more complicated, obviously, there's more infrastructure to manage, but they're very powerful and pretty popular. Then there's also libraries that will allow you to do stream processing in your own applications. The most popular of those is Kafka Streams. And this is a Java library that you can pull into any JVM application, so you can put it into your microservices, and allows you to do stream processing much more easily in your applications that you deploy wherever you want. So this is what we'll be trying to mimic here. We'll actually do some of the things that Kafka Streams can do in Java through its DSL. We're going to do some of those with just Python, just a small subset. But there are some simple use cases and common ones that we can handle without a library at all. Oh yeah, there's more libraries out there too. There's actually some already out there for Python as well. But like I said, for the whole world in general, as far as Kafka goes, Kafka Streams is the most popular. Now back to Apache Kafka. Since that is the core technology of this talk, I want to do a brief primer on Kafka for those who aren't familiar with it. I would ask you to raise hands if you use Kafka already, but I couldn't see your hands anyway. So this was just pretend that you did, and there was a mixture of some sort. And I'm not going to change my presentation at this point. So, all right, so let's go. So at the heart of Kafka is a log. All right, these logs live in the broker. The broker just basically all it does is manage logs and receiving data from them and serving up requests of data from it. So these logs are immutable. Their data comes into them one record at a time. It's never changed. It's assigned to a certain position. That number down below there, that's the offset. That position doesn't change for it as long as it exists in the log. They're append only. You can't change the order or insert them or shuffle them like that. Just keep on adding to the end. And they're ordered, so the data will be consumed from the topic in the order that it was written to the topic. And they're durable, and that's a really key point. So as data is read from this topic and processed, it's still there. It stays there as long as we want it to, and we set the retention thresholds either in time or in size on disk. When those thresholds are reached, then the older events drop off. But they're there, like I said, as long as we want them there, so we can be replayed, they can be used by other services, other applications can use the same data. Now, when we talk about this data, I like to think of them as events, and that's why I titled it event streaming. Other people just say they're just data records. So you might have heard the term event, record, or message, those three terms, and they're all interchangeable. They're all accurate with just different connotations. And here's what they look like, just a random sample. This is what an event or a record in Kafka would look like before it goes to Kafka. When it's in Kafka, it's just bytes. So it's serialized to bytes and deserialized on the other end. But normally you'll have these pieces in it. You'll have a timestamp. Every event has that. It's either assigned, you can set it yourself when you're creating the record, or it's set automatically for you. Then you have a key and a value. The key is generally a simple data type, and the key is important because it's used for ordering. We'll talk about partitions in a little bit, but when we do, keys are really critical for how things land in a partition. And then the value is usually your payload. So I show here it's like a JSON object, but it could be anything. You could be using protobuf. You could anything can be serialized to bytes. But these are the key pieces that you'll have in every record that comes into a Kafka topic. And the thing that puts those records on the topic is the producer. Now, producer is part of a client library. And this is where different languages come into play. Kafka is written in Java and Scala, but there are client libraries in lots of languages. The one that comes with Kafka when you download it is a Java client or JVM client. But there are clients for Python, Go, .NET, Node.js, a bunch of others. There's even a Haskell one. So the producer writes these events to the log one at a time. The producer is the one that is the piece that knows where they should go. So if there are multiple partitions, which actually I haven't talked about it yet, but when we do, the producer determines which partition to put each event on. It also handles things like compression if you set that. It also handles retries. So there's quite a bit of smarts in the producer. But it just keeps on appending these events, and the consumer, which is another part of the client library. These are just classes in a library. So the consumer is the one that will read the events from the log and let you process them. So you include this in your application to read your data, and then you do whatever you want with the data. And the producer and consumer don't know anything about each other. They're completely decoupled. The producer produces and doesn't know if anyone's going to consume it or who's going to consume it. There could be multiple different consumers, and the producer doesn't know or care. The consumer doesn't know where the data came from. It just knows when there's data there, I'm going to grab it and do something with it. If there's no data, it'll wait until there is. So the consumer keeps track of what it's completed, though. That's a really important feature here, that periodically it sets a committed offset, which will record the offset of the event that it's just most recently completely processed. Now, you can do this manually, or you can have it set to do it periodically. And this is important because if that consumer ever goes down, the producer, first of all, will keep on going. It doesn't know anything about it. But when the consumer goes down, it'll use that offset when it comes back up. When it comes back up, it looks at the committed offset. It says, OK, the last one I finished was 3. I'm going to go to 4 now. And so that way, you never skip data or lose data when you're using Kafka and have it configured properly. The producer, in the meantime, has gone on and done a whole bunch more. So you will, at this point, have a lag, and there's a metric you can monitor for that to see if there's a lag in what's being consumed. But that's beyond the scope of this talk. So that's the consumer and the producer. Another thing about the consumer is that they operate in consumer groups. And now we'll talk about partitions. That log I mentioned that makes up the heart of Kafka is actually a partition in a topic. So every topic is made up of partitions. You can have a topic with one partition, but usually you'll have multiple partitions. And this is what provides the scale that Kafka is famous for. You can have hundreds or thousands of partitions, and that means that workload can be spread across that many different servers. It can be stored on that many different brokers and served up by that many different brokers. It can also be consumed by that many different instances of your consumer application. So to do that, you use consumer groups. And consumer groups will manage all the instances of a given consumer application using a group ID. It'll keep track of those and balance out the workload. So here we have 2 instances of our application and 4 partitions in our topic. So each instance gets 2 partitions to work with. If we get busy, we want to scale out, we add 2 more instances, and now they each get 1 partition. When things slow down again, we can just go back and it'll rebalance it again. So the rebalancing is handled automatically for us as we add instances. Now in this case, we could add a 5th instance, but it wouldn't do anything because the data in a single partition cannot be split among multiple instances of the same consumer application. If we did that, then the ordering would be thrown off, and ordering guarantees are pretty important in Kafka. Now I mention that because ordering is based on partition. When you set the key that I showed earlier, the key will determine which partition the event will land in. So what happens is a hash is made of the key, and then that's moduloed with a number of partitions. So in this case, 4. So every event would be assigned either 0, 1, 2, or 3, and it would end up in one of those partitions. And it would always be the same one for that key. So all events of a given key, like say a customer ID or an account number for a banking application, you can guarantee that those will always be in the same partition, and therefore always consumed in order. And I think that's it for our Kafka primer. So I mentioned this, the consumer and producer are part of the Kafka client library, and there are client libraries in lots of languages. The ones I mentioned here, there's one called Kafka Python. It's a community-based library that you can find on GitHub or on PyPI. There's Confluent Kafka. Now, Confluent is a company that was founded by the original creators of Kafka. It's a company I used to work for last year. And they have a library that's really good as well. That's actually the one I'll be using in my example. And then there's this AIO Kafka, which is an async library, which I haven't tried yet, but I've heard good things about it. And there's others too. Oh, I didn't have to have myself. So these libraries, we'll be using this one in the middle for our examples in a second. But they all have basically the same things. They all are going to have some type of a class representing the producer and the consumer that you could use those in your applications. And here's an example of what they look like. Hopefully that's readable. So we're just going to import this producer class, and then we're assuming some external thing is giving us some data, and we're going to produce that to a Kafka topic. So we get this delivery update we receive from some other service, and then we create, actually I should have done this the other way around, but anyways, we can create an instance of a producer, and the producer constructor only needs, it takes a configuration dictionary, and there's lots of things you can set in it. There's only one thing you have to have, and that's the address of a Kafka broker. And so that's what we're giving it here, just the bare minimum, tells it where it can find Kafka. And then we just call the produce function on it. And the produce function takes the topic name, and then the value, and a key. So the key we're using is our driver ID, and the value is the whole event packet itself. And that's really the common thing that you'll see is that the key is actually a field in the value. And sometimes you might get a value without a key, and one of the first steps you do in stream processing is to grab a field from there, turn that into the key, so you have something to use from then on. Because for any effective stream processing, you have to have a key, especially when you're working things, aggregations or joins or things like that. You need to have something to group by. And then we just call producer flush, which finishes up the process. Now, flush we normally would call if we do a whole bunch of produce calls, but I'm only doing one here. So it's just a real simple example of like a hello world producing data to Kafka in Python. Now, consuming it is similar. We just create the consumer. This takes two required parameters or two required entries in our dictionary. It needs to have the location of a Kafka broker again, but it also has to have a group ID. Even if we're not going to use more than one instance of our application, we still need to have the group ID. But having that will make it so that we can run multiple instances, and they will automatically operate in a group like we saw earlier. And then we just jump into a loop, and we start consuming. Oh, no, I missed a step. Yeah, so when we showed earlier, the producer, you tell it the topic you're producing to. That's one of the parameters in the produce call. With the consumer, you could be consuming from multiple different topics, so you don't tell it the topic when you're calling. You just call poll, and it will poll all the topics it's subscribed to. So this next line we have down here is we call subscribe. So you subscribe to a list of topics. In this case, it's a list of one, but it could be multiple. And if you have multiple topics, it will just round robin through them as it calls poll. It'll keep checking each of those topics to see if there's any new data. The value put in here is a timeout. It just tells it just how long to wait if it doesn't receive anything. So if there's no new data, it'll wait that amount of time, and then it will return none. If there is data, it returns it as soon as it gets it. So it doesn't slow anything down to have this value higher. It just gives you, if you know that your data is not coming in quickly, you can set a higher value there and have a little bit less network traffic. Then we just grab that event. And in this case, we're going to take the value, and we have to decode it because it is coming as a binary coming from Kafka. So we decode it to string, and then we just turn that into a JSON object, and then we do something with it. So again, it's a real simple example. There's usually a lot more that you do when you're processing data, but this is the basic process that you would do over and over in different ways for different situations. So it really is easy to use Kafka from Python. I've done a lot of this with Java, and the Java examples are quite a bit noisier. Okay, but now let's talk about stream processing. So that's just the consuming and producing, and you can do a lot with that. But often, when the data is coming in, especially if it's coming in, quickly and a lot of data, you want to do some kind of processing or transformations on that data as it's flowing through. And for that, we use stream processing, which basically is just doing what we just did there, but in a continuous stream. So data is constantly flowing through, and every event that comes into the topic is going to get the same process done to it. Something's going to happen. It's going to be written to an output topic, and something's going to take on from there downstream. The basic process is input topic, do some processing, output topic. Now, I mentioned that we're going to kind of modeling after some of the features of Kafka streams. So I'm going to show how in Python we could do some of the simple things that you can do with it, some of the things you can do with the DSL in Kafka streams. So first example, we're going to do a filter. It's a pretty common operation. When you have a lot of data coming in a stream, you don't always need all of it. So you want to filter out the data that you're really interested in, and the rest can just be ignored. It doesn't go away. Remember, again, topics are durable, so the data stays there. But you filter it and then write to another topic, and the new topic will only have the data you're interested in. So to do that, all we do is we subscribe to our input topic, and then we jump into our loop, and then we just check a predicate. It could be a value of a field, it could be a combination of values in a combination of fields in the value, or it could be something external that you check. But you do something to check your predicate, and then if it matches that, then you produce it to your output topic. If it doesn't, you don't. And that's simple. Another simple one is branching. And this is a fun one, too. This allows you to take one stream and split it into multiple streams based on something in the data. I worked at one company that did this where we had a fire hose stream, we called it, and we had all the events for this company came into this one stream. And then we had a series of branches that would split it out to different streams based on some data in the event itself. So it's similar to the filtering, except it's for multiple things. So we have we subscribe to the input topic, we start polling, we check the predicate. We have two predicates here, A and B. If predicate A matches, we write out to topic A. If predicate B matches, we write out to topic B. And if we have a default one, it doesn't match either of those, it goes into the default topic. Now, you don't have to have that last step. You can just filter the ones you want to the branches you want and ignore the rest. It's all pretty flexible, and you can break this out to as many different topics as you need to. And then the idea would be then you would chain together other operations for those other topics. Those would be input streams to something else. A common thing you'll see in streaming operations like this is that the output topic for one process becomes the input topic for another process, and then you chain them together. So another example is a map, which just basically allows you to do something. The Kafka Streams DSL has a map function which allows you to do some kind of a lambda or something on every event going through the topic. So we just do the same thing here. So we create some function. Well, first we subscribe to our input topic. We define some function we want to call, and then we go into our loop. And then for every event, this one we're checking to make sure it's not none first. We just call our function on that event. And I didn't put it in here, but then after that, we would take the results of that, write it to another output topic. I should have put that in there, I'm sorry. I'll fix that slide. Really, each of these should end with writing to an output topic. So that's the full flow of any stream processing module is input, process, output. These are all stateless operations. These are the easiest ones to do without any help from any library. As we'll see a little bit later that the area where libraries really help is with the stateful processing, which we'll look at some of those things now. And our first stateful operation we'll take a look at is count, which is, again, is another kind of a hello world of stateful streaming operations. So the goal of count is basically to count by a key the values coming in your stream, or the events coming in your stream. So how many events for this given key are coming in, and you're going to get a count of those. So we just go into our loop, we pull. Here we've set up a dictionary ahead of time just called counts, and then we check if the key is already in the counts dictionary, then we'll go ahead and grab that out of the dictionary and increment its value by 1. If it's not there, then we'll add it to the dictionary and set the value at 1. So again, really simple, straightforward, but you can do quite a bit with this basic principle. And then we produce the output of that to another topic using the key and then the current count. Next one we'll show is sum, which you'll see a lot of similarities in all these, but basically, again, we're going to use the dictionary, and we're going to check to see if the key is there. If it is there, then we'll use it, and we'll add the value from, usually wouldn't be the full value, probably be a field in the value, but you grab that and you add it to the one that's already in there. And if it's not there already, then you go ahead and add it to the dictionary and set it the value as the initial one. And again, produce that to another topic. And then aggregate, which is similar to sum but broader, you can do more things with it. Again, that's another function in Kafka Streams. And streaming libraries like that will usually have some type of a group by thing first that they'll do to manage that. Here we're just using the dictionary to keep track of our groups. So this one we set the key for the aggregate, we set it to the aggregate function. So we call it whatever function we're going to do to do our aggregation, whatever it's going to be an average or whatever we're going to do. And we pass in the key, the current value of that dictionary for that key, and then the event value. In this case, we're not doing the check first because if it's none, that's okay. It'll just use the event value. Our aggregate function will handle that behind the scenes. And then finally, we do produce to the output topic again. And now this is probably the most complicated of the ones that I would attempt to do even without a library, and that's a join. So this is when you've got two streams of events coming in, basically two topics, and you want and they have a common key, and you want to join the values from those two topics into one new value. So the way we're going to do this is we're going to set up 3 dictionaries, A, B, and C, and then we also have our consumers, 2 different consumers we're using. We could actually do this with one consumer subscribed to the 2 topics, but it was clearer in the code to do it this way, I thought. So we're going to start in our loop. We're going to first consume from, we're first going to call consumer A. It's going to call its poll. We're going to get an event from that. We're going to check to see if that event is in the A, we're first going to add it to the A dictionary to make sure it is there for future use. And then we're going to check to see if that key is already in the B dictionary. And if it's not in the C dictionary. The C dictionary is going to be our target dictionary. So if the A key is in the B dictionary and not in C, that means we need to go ahead and do our join. So then we do our join function. Oh, jumped ahead here. Our join function is basically going to be a function that takes the 2 values and merges them together. So it's going to give us our end result. Maybe we want to pull a few values from each of these different, few fields from each of the different values and put them together into a new value. That's where we have that logic. So we call our join function, and we give it the A event that just came in, and the event from the B dictionary that we just looked at. And then we add that new event that has the combined values, we add that to the C dictionary. Then we go through and pull the B event, and basically do the same thing for that one. Now, so the idea here is we don't know when these events are going to come into each of these topics. It may come to B first, it may come to A first. There may be some delays in there even. So by storing this in the dictionary, that gives us a chance to go find those later, even if it's several minutes after the first one. Now you can set things like thresholds of time for windowing if you need to do that. That could all be done just with Python code as well, but it wouldn't fit on a slide. So the basic idea is, though, that we have to use these dictionaries to hold our interim state. That's the key thing with stateful stream processing is you need to have interim state where you can keep track of stuff that's been happening, because what happens with each new event depends on some other event that may have already come through. And in the end, we produce the output of our events to the C topic, output topic. So our input topic, we have 2 input topics in this case. We did 1 input topic that has the combined values of those 2, matched up by key. Okay, so now I think we're ready for a brief demo, which I hope will work. I'm tethered with my phone here, which doesn't have a lot of signal, but we'll see. So what I did for the demo, let me just look at the code first. What I have is I've got a process that's reading tweets off of Twitter that have stir trek in them. So it's grabbing all those, feeding them into a Kafka topic, and now we're going to run this process against that. So this is our tweet processor. It's just a simple Python application. We're using the techniques we talked about earlier. I'm using a dictionary to show our tweeters and their counts. And then I've got tweet IDs. So these are IDs of individual tweets that we've seen already, because the process I have loading the tweets is producing duplicates, and we don't want to duplicate the counts. So we've got our producer and our consumer, and I've got these configs. I just have them in a separate Python file with the dictionary that just has all my configuration values because they're not really important. And then the serializer we'll have to use for our integer for our count. Okay, so we're going to subscribe to the input topic, which is the topic that has all the tweets in it. And then we're going to start polling. And if there's any data there, we will take that data, load it to a JSON object, which represents the tweet. We'll grab the ID, and then we'll check to see if that ID is not already in our tweet IDs list. If it is not, then we will, if it's not, then we'll add it to that list so we can not catch it again later. And then we check to see if the user from that tweet is in our tweeters dictionary. And then if that is, then we'll go ahead and increment their count. If they're not there yet, then we'll add them and we'll set their count to 1. So this person just tweeted about Star Trek first time, so they get a value of 1 in the dictionary. And now as these flow through and we keep on checking them all, it should be accumulating a count. And then we'll produce that to an output topic. And then we have this dashboard app over here, which is just a Flask app that's going to consume from the output topic, and it's going to display our counts in a little web page. So let me see if I got these running. Whoops. That was running. Okay, so this is our tweet processor app. I'm just going to launch that one now. Hopefully it will work. It looks like it's getting data. And then I can refresh this. Something odd happened because these numbers were a lot larger. There it goes. Okay, that's where they were at. So keep tweeting, and if you start tweeting a lot, you'll show up on here eventually. So it looks like Sarah is the current leader. So that's being produced by that tweet processor application. Come on, people, you're not tweeting enough. Yeah, it really does help. As a former conference organizer myself, it really helps when you put on social media, Twitter, LinkedIn, Mastodon, Blue Sky, whatever you're on, about these events, because it really helps get the word out for the next time. I was just at a local event here in Columbus, a little tech gathering, and I was surprised that none of the people that I met with knew about Star Trek today. So we got to do a better job of getting the word out. All right, so that's the demo. Now, let me go back to the code real briefly on this. So the key thing here is that we're using these, for the interim state, we're using this dictionary and this list. And the problem with these things, and this is the challenges with stream processing, the way we're doing it, is state and scale. Those are the two main problems that you run into with stream process, especially stateful. Even with non-stateful, the scale is still an issue. But the state is an obvious one. Any variables that we use to hold interim state are going to go away when our application shuts down. So we're going to lose the interim state. So if we're trying to do our joins, we might shut down after topic lands in, or event lands in topic A, and we shut down, and we start it back up again, then it lands in B, and A is not there anymore. We're never going to make that join. So maintaining state between shutdowns is a key issue. And that's one of the things that the stream processing libraries will help us with. So they'll have ways of writing a state out, like for example, Kafka Streams uses RocksDB. Others use different state stores, but you have some type of, even if it's just file on disk, you have some type of a permanent state store that will hold that data in case you shut down and restart again. And then the other issue is the scale. Remember we talked about the different partitions in a Kafka topic, and you can have multiple instances of a consumer. Well, you can also have multiple instances of a stream processing application. Each of those is a consumer, and they'll operate in a consumer group, but that means each of those applications will be getting only part of the data, and that might not work for the aggregations or joins or things you're trying to do. So you have to figure out how to keep the track of the scale across those different partitions, and also then to join that back up together to get your end results. So those are the challenges that you run into with doing stream processing, like I said, simple cases like we're showing. Now, with that said, there's a lot of situations where that's not an issue. So I mainly wanted to do this talk because I think that stream processing is a really powerful tool that we can all use, and as Python developers, is one that a lot of us don't know is out there to use. I've been surprised that, I mean, a lot of Python developers who have a use case for this and didn't know about things like even about Apache Kafka. So you use these things together, there's a lot that you can do, and you don't necessarily have to have something like a Flink or KSQL or even a library. There's a lot of things that you can do to handle simple use cases just with Python code. But with that said, there is these challenges, and so there are some stream processing libraries out there that will help you with this. Like I said, there's Kafka Streams in Java, and that's very popular. If you're in a Java shop, just use that. There's really nothing else to look at. In the Python world, there's a few options out there. Faust has been around for a while. It's debatable how well it's being maintained these days because it was started by Robinhood, I think, and they kind of dropped it. And it's being, I think, picked up by the community, but I'm not really sure where that's at. You can roll your own like we were doing there. Or we have a new library that our company puts out. It's fully open source called Quick Streams, which I'll show you a bit of that, since I guess I do have time. I'm going faster than I thought. But the key thing that these libraries will all do is, like I said, is they'll help you to manage the state and scale. So as you scale out to multiple partitions and multiple instances of your application, these libraries will help you to manage all that, or will manage it for you, so you don't need to worry about it. So here's on a slide just an example of what a Quick Streams looks like. Again, it's just a library that you import into your application. And you import this instead of the producer and consumer, so you don't need those pieces that are encompassing it. And most of the libraries work the same way. Kafka Streams does that as well. Kafka Streams doesn't need, when you're using Kafka Streams, you don't need a producer or consumer. It does both. It plays the role of both. So we import that, and we create a Kafka streaming client. And that's going to be the root class for everything else that we do in here. And that just needs the address of the broker. And then we get consumers that are out of that library, out of that client. We'll get a consumer and a producer. And so we give it the topic name for the consumer and the consumer group, and then just the topic for the producer. And then it's going to just go through. It's got some callbacks. So we have a receive handler that we're going to do something with. In this case, we're receiving the food delivery data that we showed in that slider at the beginning, and we're going to call a function that calcs the ETA of that, and we're loading it into a data frame. One of the cool things about Quick Streams, which I don't show real well in this talk, but it has really tight integration with Pandas data frames. So you have your data coming right into, instead of having to do the parsing of data with JSON, things like that, you can have it just go right into data frames and work with them that way. This also helps you with a lot of things like joins. It doesn't have operators for joins like something like Kafka Streams has, but you can use data frames for that as well. And a lot of other things that you would normally do with data. So here we're taking this data frame, we're going to add a new column to the data frame by calling this calc ETA, taking the data from our stream. And then we're going to produce that back out to an output topic. And just pass the whole data frame in as the argument to our publish instead of produce. And then we assign that handler to our on data received from that stream. And then once it's all set, we just call this app.run. And that handles our loop for us, and it's a lot cleaner than just a while true. It'll handle clean shutdowns and things like that for you as well. So there's a lot more in there that the library does for you, and I want to show real briefly back in the code how we would do the same tweet processor with Quick Streams. So here we would just get our Kafka streaming client like I just showed, set up our producer and our consumer. And here, instead of that dictionary and our list, I'm going to use this quick local file storage. Now this will manage the state for us. So by putting tweet count into local file storage instead of into a dictionary, if we shut down, it's all written to disk and stored and reloaded when we start back up again. And same thing with our list for the tweet IDs. The rest of it's pretty similar. We get the tweets coming in. This is our handler again. So this is going to be this handler is called for every bit of data that comes through the stream. So it's going to grab that. It's going to convert it to JSON. And then we're going to set up our producer. And then we're going to just, again, check to see if it's already in the store. Instead of a dictionary, we're going to check to see if it's in our local storage. And if it is, we're going to increment the value If it's not, we're going to add it and set the value to 1. Now you see here for the tweet IDs, I checked just again to see if it contains the key. So that's basically to say if it, like the in. I'm checking that there, then I'm adding it to there. Now, local storage is structured more like a dictionary, so I give it a key and a value. I just put a value 0 here because I don't really care about the value in this case because I'm treating it more like a list. But again, it will store that for me. So with the other structure I had, if I ran it again, I would get duplicates because it wouldn't be matching all those. Or potentially I could get duplicates. Anyway, so that'll manage the tweet IDs list. If we shut down, it'll retain it for us. And then the rest of it works pretty much the same. We just publish that event, and then we set up the handlers there, and then we do the app.run. So that's how you do the same code that we did for our top tweeters web app. We would do that same thing with the stream processor, and it would handle that. Now this way we could run multiple instances of our tweet processor. If I ran multiple instances of that other one, it would get all kinds of inaccuracies. And the way that this handles this state or the scale is, if I can find it here, right in here. When I create this producer stream, I do a stream ID equals tweet user. What this will do is it creates a logical stream for every user ID. So basically, it handles the separation. Every tweet ID that comes in will be in a certain partition. So if I'm using the stream ID, it'll make sure that the processing is always happening on that same partition. You might have multiple streams, logical streams in one partition because there's multiple different keys in that partition, but they'll always be the same partition. So that'll make sure you keep your ordering no matter how many different times you scale out. As things rebalance, the stream ID always stays with whatever partition or whatever instance of your application is handling the partition that your key is in. So this, the stream ID handles the scale, the local storage handles the state, and then from then on, you again just basically use Python or libraries like Pandas or other tools that are available in Python. Python's great with working with data, so you really don't need to have a DSL or other things built into the streaming library. This just handles the problem points, the state and the scale. And that's with quick streams. And I guess I'm running short. So I have time for questions if there are any. Let's go back to my slide deck. And then that was it for my presentation. Now, this QR code here this is your opportunity to win a $50 Amazon gift card. So just scan that QR code, or if you miss that chance now, you can scan the back of my shirt later on. I'll try not to wear my backpack throughout the rest of the day. But scan that code, and you can fill a little form and enter a contest to win a $50 Amazon gift card. I'll announce the winner tomorrow on both Twitter and LinkedIn, and also email you directly whoever won. But I also will be using that app throughout the day, so I will be posting who the top tweeters are. So if you want to become famous, go ahead and start tweeting more about Stir Trek, and you'll show up on the leaderboard. And with that, I think that's all I had. Thanks.